The ice at the top of the world just did something scientists thought was still decades away. At the bottom of the world, the ice that was supposed to be the stable one just started falling apart on its own separate timeline. Two completely different systems, governed by two completely different sets of physical rules, failing for two entirely different reasons. And at this exact moment, both are happening together. The Arctic just posted its lowest winter ice level in 47 years of satellite records. Antarctica, after decades of looking almost immune to the changes reshaping the rest of the planet, has tipped into a decline researchers themselves are calling a genuine surprise. Here's what's actually happening at both ends of the Earth, grounded entirely in peer-reviewed research published this year. Start at the top of the world. Arctic sea ice has been shrinking for decades. That part isn't news. What is news is what happened to the data between roughly 2005 and 2024. Arctic winter sea ice, the thick cap that grows across the frozen ocean every year, stopped declining. It plateaued. Year after year, the winter maximum stayed low compared to the 1980s, but it wasn't falling any further. Some researchers even floated the idea that winter ice had entered a kind of holding pattern, a pause built into the longer decline. Here's the thing about that pause, though. It was never a recovery. It was a slowdown, sitting on top of a much longer trend. The planet kept warming. The ice stayed thinner than it used to be. It simply wasn't shrinking any further for a stretch of years. Then 2025 arrived, and the pause ended in dramatic fashion. Between the winter peak of 2024 and the winter peak of 2025, Arctic sea ice extent fell by 5.8% in a single year, the largest year-over-year winter drop ever recorded in the satellite era, a record stretching back to 1978. That number might not sound dramatic in isolation, but Arctic winter ice normally spans somewhere around 14 million square kilometers. A 5.8% drop translates into an area of missing ice roughly twice the size of Texas, gone within 12 months. What actually rattled the scientific community wasn't just the size of the drop, it was the timing. Ice should have been sitting at its annual maximum right around that measurement, the single point each year when the ice cover is supposed to be at its thickest. Instead, it was sitting at levels nobody had documented in nearly 5 decades, at precisely the moment it should have been strongest. Researchers led by Dr. Duo Chan at the University of Southampton, working alongside the National Oceanography Center, went back and built simulations to test whether a drop that steep was even physically plausible, running the numbers against decades of climate model output. What they found was that matches for a drop this severe existed in the models, though they were genuinely rare. And the simulations captured something the team hadn't specifically anticipated going in. The following winter, 2026, ice cover ticked up slightly from the prior year's record low, a small partial recovery, and the model runs reproduced that small uptick almost exactly. Here's the part that matters most. In every comparable case the models produced, a drop this steep was rarely reversed afterward. The system doesn't snap back to where it started. It tends to settle into a lower band and fluctuate around that diminished level for years at a stretch. The small recovery in 2026 wasn't the beginning of a return to normal. It was Arctic sea ice finding a new lower baseline to wobble around. As Professor Simon Josie of the National Oceanography Center put it, current data suggests winter sea ice coverage will likely keep fluctuating around these lower levels for the next several years, rather than climbing back toward what used to be considered normal even a decade ago. That finding directly overturns the argument that had built up around the so-called pause, sometimes made in good faith and sometimes used more selectively, that Arctic ice loss was leveling off on its own. The new research makes the opposite case, using hard numbers. The pause was a temporary lull, not a genuine stabilization, and the moment conditions aligned the way they did in 2025, the decline resumed exactly where the longer-term trend line had left off, just compressed into a single violent year rather than spread gradually across several. NASA and the National Snow and Ice Data Center independently confirmed the broader pattern. Arctic sea ice reached its annual maximum on March 15, 2026, at just over 14.29 million square kilometers, statistically tied with 2025's maximum of 14.31 million square kilometers, 2 consecutive years now sitting at the very bottom of a 47-year satellite record. So what actually happens as the Arctic runs progressively lower on winter ice? Most people picture the Arctic crisis as a summer story, shrinking September ice, stranded wildlife, visible melt under direct sunlight. But winter ice is doing something summer ice simply can't. It functions as a barrier, separating an ocean that sits relatively warm, still above freezing, from air above it that can run 60 to 70 degrees colder during the darkest stretch of the year. When that barrier stays thick and continuous, heat and moisture stay locked inside the ocean where they belong. When it thins out or develops gaps, heat escapes into the atmosphere throughout the winter. That extra energy doesn't simply stay parked over the North Pole either. It shifts pressure patterns and feeds directly into the jet stream, and atmospheric scientists have increasingly linked it to the kind of extreme cold snaps and disrupted storm tracks that show up thousands of miles south, in places like the American Midwest or Northern Europe, in the dead of winter. A thinner Arctic winter cap isn't just a regional data point, it's a lever with reach extending deep into the weather systems everyone else lives under. The underlying mechanism comes down to something called albedo, and once it clicks, satellite images of polar ice stop looking quite the same. Ice and snow are bright, reflecting sunlight back into space. Open ocean water is dark, absorbing sunlight instead. When a patch of sea ice disappears and open water takes its place, that patch of ocean stops bouncing sunlight away and starts soaking it up, warming the water underneath. Warmer water makes it harder for ice to reform the following winter, which exposes more dark ocean the year after, which absorbs even more heat in turn. It's a feedback loop, quite literally the planet's own reflective thermostat running in reverse, and it's a central reason the Arctic is currently warming at close to 4 times the global average. Now fly to the opposite end of the planet, because while all of this has been unfolding up north, Antarctica has been writing its own entirely separate story. For most of the last several decades, Antarctica looked like the exception to everything happening in the Arctic. While northern ice steadily shrank, Antarctic sea ice held roughly steady, in some years even expanding slightly. That genuinely puzzled scientists for years. How could one pole be melting while the other appeared stable? The answer comes down to basic geography. The Arctic is an ocean surrounded by land. Antarctica is a continent surrounded by ocean, and that difference matters enormously. For decades, Antarctica had real protective buffers. Cold meltwater running off the ice sheet formed a layer of fresher, colder surface water, and strong circumpolar winds kept the whole system relatively stable and insulated from the kind of rapid loss unfolding in the north. Then, in 2016, that insulation broke. Antarctic sea ice extent, which had been gently trending upward or holding flat for nearly 4 decades, reversed almost overnight and began falling sharply. It hit a record low in 2022, broke that record again in 2023, dropping to an extent so far below the historical average that the missing ice alone covered an area larger than the entire landmass of Greenland. Researchers were left facing an uncomfortable question: what specifically changed in 2016 that flipped one of the most stable ice systems on the planet into one of its most volatile? A team, again working out of the University of Southampton, published findings this year describing what they call a triple whammy, 3 separate mechanisms compounding on top of one another to drive the decline. The first is a warming ocean surface layer that has eroded the cold, fresh meltwater buffer that used to shield the ice from below. The second is a shift in wind and pressure patterns circling the Southern Ocean, tied to something called the Southern Annular Mode, which has been running in a persistently positive phase, strengthening the westerly winds circling the continent and bringing unusually warm, wet conditions specifically to the Antarctic Peninsula, already one of the fastest warming regions on Earth. The third is a change deep within the ocean itself, a shift in circulation pulling warmer water up from below into direct contact with the ice from underneath, melting it from a direction that used to remain comparatively stable. Individually, researchers suggest each of these might have been survivable. Compounding on each other year after year, they've pushed the system into a state actively reinforcing its own decline rather than naturally correcting. Antarctica's decline isn't uniform across the whole continent either, which is part of what makes the picture genuinely strange to look at on a map. Along the Atlantic sector of the Southern Ocean, near the Antarctic Peninsula specifically, retreat has been exceptionally rapid. Other sections, closer to the Ross Sea, have stayed much closer to their historical averages. The difference traces back to a pressure system called the Amundsen Sea Low, which pushes warm air toward one side of the continent and cold air toward the other simultaneously, meaning a single map of Antarctica right now can show one region running colder than normal sitting directly beside another running warmer, both driven by the exact same atmospheric feature. There's one especially striking event worth understanding in detail, because it shows just how far the system can swing. In the middle of the Antarctic winter of 2024, during months when parts of the continent sit in near total darkness, and temperatures typically stay well below freezing, East Antarctica experienced a heat wave that defied existing climate models. Temperatures in parts of the region spiked as much as 28 degrees Celsius above the seasonal average and stayed elevated for more than 2 weeks straight. Scientists studying the event reached for a comparison to make that number graspable. An anomaly of that scale striking the United Kingdom in the middle of January would push temperatures there into the mid-30s Celsius, essentially a summer heat wave, landing in the dead of a British winter. That's the scale of what happened in East Antarctica, during a season when the sun barely rises at all. Researchers who studied the event afterward attributed it to a combination of factors: a weakened polar vortex that normally seals off the Antarctic interior, an atmospheric river carrying an unusual surge of warm, moist air deep inland, and record-low sea ice offshore that removed one of the natural barriers that would have otherwise blocked that warm air from penetrating so far. Climate modeling run by the same team indicated that human-caused warming significantly amplified both the intensity and duration of the event. And critically, researchers were explicit that this wasn't a one-off fluke. They described it as a preview of the kind of extreme event likely to become more frequent as the underlying warming trend continues. If a sudden winter heat wave sounds abstract, one specific glacier makes the consequences concrete. Victoria Glacier, on the Antarctic Peninsula, recently underwent the fastest retreat ever documented in the modern satellite record, roughly 25 kilometers of retreat across about 16 months, with 8 of those kilometers collapsing in just 2 months at the peak of the event. Researchers analyzing the collapse in detail, published in Nature Geoscience, traced the mechanism to a specific combination of factors. Victoria had originally fed into the Larsen B ice shelf, which broke up spectacularly in 2002. In the years afterward, sea ice reformed in the surrounding bay and thickened, effectively holding the glacier in place for over a decade, even without its original ice shelf. But Victoria's ice was simultaneously stretching and thinning across the unusually flat seabed underneath it, forming what glaciologists call an ice plain. As warmer ocean temperatures began preventing that protective sea ice from reforming reliably, storms in 2022 sent waves crashing into the glacier's margin, clearing out the remaining sea ice and shattering roughly 12 kilometers of Victoria's floating ice into icebergs. With that buttressing effect gone, the thinned ice plain began lifting and falling with the tides until it eventually floated free of the bedrock entirely and started snapping apart through a process called buoyancy-driven calving, accompanied by detectable glacial earthquakes as the ice fractured. Researchers have flagged this as a genuinely important discovery specifically because it reveals a mechanism that could apply to other glaciers resting on similarly flat below sea level bedrock elsewhere across West Antarctica, several of which hold enough ice to meaningfully raise global sea levels if they behave the same way. This is reshaping how scientists think about glacial collapse generally. Retreat that used to be modeled as slow and broadly predictable can, under the right conditions, turn out to be fast, sudden, and effectively irreversible. There's one more concept worth understanding, because researchers have coined a specific term for a scenario they're now watching for at both poles simultaneously: a blue ocean event. The term describes the moment sea ice extent in a given region falls below roughly 1 million square kilometers, low enough that satellite images would show overwhelmingly open, ice-free blue water rather than white ice. Researchers tracking current trends have raised the possibility that an Arctic blue ocean event and an Antarctic blue ocean event could theoretically occur within a similar window in the coming years, something that has never happened simultaneously anywhere in the satellite era. It's worth being precise about what that term does and doesn't mean. It refers specifically to a seasonal minimum dropping below that defined threshold, a regional and temporary event, rather than the permanent disappearance of all polar ice everywhere. But even a temporary blue ocean event at either pole would represent a level of open, sunlight-absorbing ocean water the current climate system has essentially never experienced during the period we've been able to measure it by satellite. And the albedo feedback loop means even a short-lived event like that could leave a lasting mark on how quickly the surrounding ice recovers afterward. There's also a genuinely surprising connection between these two, seemingly separate polar stories. Researchers have found that meltwater from West Antarctica can influence warming and sea ice loss in the Arctic through a complex chain of ocean and atmospheric responses. Freshening Antarctic water reduces its density, which enhances a broader system of ocean circulation that transports warm water northward, contributing to Arctic warming in turn. The two poles aren't isolated systems reacting independently. They're connected through a chain of mechanisms spanning entire hemispheres. There's a genuine paradox tucked inside this too. Meltwater from Antarctic glaciers is, for now, actually helping keep some parts of the surrounding ocean cooler, forming a layer of cold, fresh water that insulates ice above it from warmer water below. That same meltwater is simultaneously contributing to global sea level rise, and as more ice melts, that protective layer may eventually break down entirely, exposing the ice above to considerably more warming than it currently experiences. It functions, in effect, as a temporary shield, one that could accelerate the very process it's currently holding back once it finally gives way. If you want to understand what's really driving the headlines instead of just the alarming version of them, that's exactly the kind of grounded breakdown worth subscribing for, since both of these stories are still actively developing. What does any of this actually mean for people living thousands of miles from either pole? Sea ice loss itself doesn't directly raise sea levels in a major way. since floating ice has already displaced its own volume before it ever melts, the same way an ice cube doesn't raise the water level in a glass as it shrinks. The real sea level danger comes from land-based ice, glaciers, and ice sheets resting on solid rock. And any meaningful acceleration in the collapse of those specific systems translates directly into rising coastlines everywhere on Earth, not just near either pole. But sea ice loss still matters enormously because it functions as one of the primary triggers accelerating everything else in the system. Less sea ice means more dark, open ocean absorbing heat, more heat in the ocean, and atmosphere destabilizes the land-based glaciers sitting nearby, the ones that do directly raise sea levels. Reduced Arctic winter ice reshapes pressure systems that influence storm tracks and cold outbreaks across the entire northern hemisphere, and a weakened Antarctic polar vortex has documented links to disrupted weather reaching into the mid-latitudes of the southern hemisphere as well. None of this requires living near a coastline to matter directly. These shifts reach into ordinary life everywhere through disrupted storm tracks, shifting growing seasons, and the kind of unusual cold snaps or heat waves once dismissed as freak, isolated events, increasingly understood by researchers as part of a genuine expected pattern instead. The honest picture here isn't that either pole is collapsing overnight in some single, sudden event. That's not what the data shows. But something significant is happening. Two enormous, complex physical systems, each with decades of relative stability behind it, have both entered periods of measurable, mechanistically understood decline at the same time, for reasons specific to each region, but tracing back to the same underlying cause. Stability and permanence simply aren't the same thing. The system can hold steady for years, even decades, and then shift rapidly once the right combination of conditions lines up. It's worth remembering that the satellite record only stretches back 47 years, a genuinely brief window in geological terms, which means every record broken in 2022, 2023, 2025, and 2026 isn't just a record within living memory, it's the lowest point ever documented by direct instrumentation, full stop, with no equivalent baseline from before the satellite era to compare it against. That's exactly why researchers keep reaching for the word unprecedented. Rather than simply unusual, this is genuinely new ground. We'll keep tracking how both of these stories develop as new research comes in. Thank you for watching, and I'll see you in the next one.